Hello community, so great that you are back. Yes, we have some brand new research by Google about the context engineering. And of course you at the channel Discover AI, so let's have a look at the latest AI research. Google Cloud AI, University of Virginia, Compass, enhancing the agent long horizon reasoning with an evolving context. October 9th, 2025, and let's just jump right into it. They analyze, okay, if we only have a single agent system that reacts here on the react style, what we have? We have a user query, we have the thinking, or the reasoning here, and then we have the acting, so this is the react paradigm. Then we observe the result, we think again, we act again, and then after a long reasoning, think everything is great. We have a single massive notepad. The log gets written down sequentially, and after a few dozen steps, the notebook is a chaotic mess. Critically, early clues are buried under pages of irrelevant transcript, and everything is lost. Confused acting, failed premature conclusion. This is not gonna work at all. So therefore, of course, we invented a multi-agent system, mass systems, with, somehow we have to put the human in the loop, no? So either we have now a strategic template, or we just have come back and ask here for have human instruction. So we have a plan and executor, the tool use, a human intervention, we have a reflector agent, an updated context, and execute a success. But you see, we have humans in the loop. It's unscalable, it has a manual design, it is unstructured given whatever the human intervention is here. So we can't scale this. This is not good enough if we want to have autonomous agents. So of course, you know what we're going to do. We have now multi-agent system without any humans in the loop. And we have a brand new idea by Google, Compass. So let's have a look what's happening here. It is supposed to be fully automated. What could go wrong? So here we have it, Compass, a hierarchical framework that elevates the strategic reasoning and the context management now. And now the context management elements become architectural primitives, enabling, hopefully, thereby reliable long-horizon reasoning without the complexity of multi-agent topologies. And you might say, hey, this sounds interesting. Yes, of course. And you know, the authors tell us, hey, our findings highlight, after a lot of experimentation, that there's a critical distinction between the tactical reasoning, this means the capacity for an accurate tool use and an instruction following within an agent turn. And then we have the second category of strategic reasoning, our higher level oversight that guides now reflection, replanning, and even when to stop the termination decision by our multi-agent system. And you would say, this sounds so familiar. Wasn't there a video just 2 days ago? Or when you see this 3 days ago, agentic context engineering here, ACE, that is so much better than here, our entropy Pareto optimal GEPA. Yes, of course. And I told you, if you combine ACE here by Stanford University and UC Berkeley as an input here with meta superintelligence, then it becomes absolutely a two-loop system where we have in the inner loop here the agent that performs here and generates the raw data, what works and doesn't work. In the outer loop, we have ACE. The system reflects on the raw data to distill strategic higher-level principles. So you see, unbelievable. Just within 3, 4, 5 days, we have Stanford University, UC Berkeley, and now Google on the same topic. Absolutely. But let's come back to Compass, to Google Cloud AI and University of Virginia and see what they have done. Now, they approached it almost identical. Have a look. They say, hey, the ability for an agent to maintain coherence, adapt its strategy, and avoid getting lost during complex multi-step problems is what separates a clever tool from a much more intelligent, truly autonomous system. And therefore, we built Compass in this particular way. As you see here on this visualization from the authors, October 9, 2025, we have a main agent. This is our worker B. This is our beautiful B that does all the work. But you see, it has some input. And we have other agents. And we have, in principle, 2 other agents, the meta thinker and a context manager. Now, meta thinker is something you're familiar with. This is the orchestration agent, everything here for the strategic analysis, not performing here any real job, but just thinking, analyzing everything. But the real innovation, if you want, here is in the context manager. And you see here, oh yeah, that's interesting. Like an example, hey, keep API configuration and architectural decisions and drop the redundant tool outputs or old logs. And note, task 3 of 5 complete. the authorization bug is still pending to be solved, and you say, you get a first idea what's happening. So let's have a closer look to this system. Now the authors provide us here the exact prompt they used here for the main agent. Telling, hey, you're the main agent, your job is to execute the user task through an iterative loop of reasoning, tool use, and observation. You read the task, you decide one action or one tool call, and execute only one tool call at a time. We reduce the overall system complexity because AIs are not, the LLMs are not clever enough, they're just stupid, so everything has to be reduced down to one tool at a time. One tool to search, one tool to retrieve, one tool, you get it. Observe the result, repeat until complete, you have some guidelines, great. And then, of course, we have the meta syncer. Now, the meta syncer has another instruction. Now, to say, hey, you are asynchronously in parallel to the main agent I just showed you. And the meta syncer job is now to monitor another execution for strategic anomalies and completion signals. So, the meta syncer task is continuously observe the main agent actions and outputs. Then, detect anomalies such as repeated failure by the main agent, contradiction, or just wasted time or effort. Plus, detect signals that suggest that the task may already be complete. We know when to stop. When triggered now, the main syncer is now deciding whether to persist, this means allow the main agent to continue, pivot, to redirect the strategy, verify, say, hey, pause and request additional checks, go back and check again, or terminate. That's, yeah, done. And of course, what's missing is now the most intelligent one, the context manager. So what is the job of the context manager? You say, hey, you are not a context manager, little AI. You transform full task history and research notes into a concise, execution-ready context for the main agent each turn. So we immediately understand we have an input here, the full task history and all the research note. And we have to produce something, a concise execution-ready context for the main agent for each single turn. So what we have, input is the original question, all the previous node, all the structured briefs from the earlier round, all the high-level summaries, all the verified evidence, all the constraint that we discovered up until now. And then the current research progress, our tau, our trajectory, the turn level trace, the reasoning trace, including the key observation, the tool result, all the reflections that we have, what is working, what is not working. And of course here, the meta decision. The main thing here by the meta agent, should I continue, reflect, replan, verify, or stop? Our primary decision points. And then we tell our context manager, hey, you produce a single output. Produce a structured context X for the main agent, concise, specific, directly actionable, and use the following sections. Task, a one-sentence restatement of the human query. Second, the most recent evidence, 2 to 5 bullet points of verified relevant facts. Cite tool names, sources, whatever. Third, critical constraint and all the corrections that we found. Means formatting, grounding the constraints, any correction to the earlier mistakes. 4, any open items. Anything that is unresolved sub-questions or missing data, prioritize the listing. 5th, the next action. Look at the plan. This is what you have to do next. 2 to 4 concrete steps aligned with the decision, tools to call, targets to acquire, success criteria whenever you can decide, hey, I fulfilled my job. 6, tool hints, specific tools to use that are really available for you on the net, internet, whatever, subnet. Great. So you see, we have all the prompts for all the agents, so let's do this. Let's jump into the details. And if you prefer to have this here on this simple flowchart, okay, no problem. So as I told you, we have a worker B. At the start of each major turn, the main agent receives a fresh, concise, and structured context brief from the context manager. No? Here's the input, and the agent says now, hey, I can focus on a single complexity reduced trivial task, only calling one tool, only doing one thing at a time, because I'm a stupid AI agent. Great. So this brief now tells exactly what its current objective is, the most relevant fact it needs, and what its next action should be. And the main agent keeps it all now focused on agile and everything is great. And you might say, okay, but who is supervising now the main agent, the thinker or the context manager? Haha. Now the thinker job is not to perform actions, but to engage in the high-level strategic overall reasoning. So it watches here for specific anomalies, no? Like we've seen in a prompt, for looping behavior. No? Is the agent trying to the same failed search query repeatedly and always failing, continues to fail? Interrupt. Or we have a constraint drift. Did the agent simply forgot a critical constraint from the original prompt? No? Then remind him, like the array must be from whatever. Or task completion. Has the main agent here gathered enough evidence to confidently answer the question, what is the stop criteria? So those are the jobs here of the meta thinker. But of course, the most beautiful job, before we go there. So meta thinker has here also signals. It detects the anomaly or potential conclusion, issues a high-level strategic signal. Here we have them. Signals are simple, like continue, pivot, do a new plan, verify, double check, or terminate. Ready, conclude. And those are now going to the context manager. And this is here the most beautiful agent of all. The context manager job is to ensure that the main agent has all the perfect bite-sized briefing to work from. So context manager takes care that the main agent has really a real reduced complexity to work with. Context manager synthesizes now a new context brief for the main agent. It draws here primarily from three sources. No? The persistent structured nodes from all the previous turn, whatever we know. The full message trajectory of the main agent's most recent action. What have I done? Where am I standing? What have I already performed here in the labyrinth? And the latest strategic signal here from the meta thinker. Because if the meta thinker decides, hey, I just watched, I've seen your latest result, you're good to go. We have a termination. We do have a result. I think we have a high enough probability that we can say this is a verified answer. Then we have here the termination command. Great. As you see, we have an interesting, I don't want to say loop system because this is the next one, but you see, it's not easy that everything is connected here to the main agent, but the context manager is the overarching agent over the main agent and takes care that our little worker bee, our main agent, can do all the work and is not overwhelmed with too much data, with too much complexity, with too much jobs, with too much, you get it. Now, if you look at this and you know immediately, hey, there are two loops. No? You have an inner loop, a tactical loop. No? The main agent fast-paced React cycle here, where it executes several tool calls based on the static brief it was given here by the context manager. But of course, if we include now the meta thinker, you see we have a strategic loop. No? Because if we have now those three agents here, we have a slower turn-per-turn cycle. No? After the main agent completes a turn, the meta thinker makes a strategic decisions. Already done yet? Finished? Yes, no. Verification necessary? All the reflections are green? The context manager then creates a new updated brief and the main agent begins a fresh inner loop. So this is, if you want, the evolving context function here from the title. And this is governed here by the algorithm 1. The inner loop is the algorithm 2. And you want to see this here. Here you have it here from the paper. Algorithm 1 is the outer loop, the strategic loop, and here you see we have nested algorithm 2, just that you have it compatible if you read the paper. And algorithm 2 is, of course, here the inner loop here of the tactical reasoning. So you say, wow, they are absolutely here symmetric to what we already know from ACE. No? At first, let's have a look at the result. How good is it? Now we have, the authors decided here, Google decided here to go with here 3 different benchmarks, Gaia, Browse Comp or BC, and Human's Last Exam here, great, 2025-24. Now they go here in general here with a Gemini 2.5 Pro and a Gemini 2.5 Flash here for the reasoning process. Single agent, great. For the tools, you have here which tools were available here to our single agent. You have search tool, coding tool, terminal tool, browsing tool, syncing tool, context tool for databases and whatever. Great, this is it. So these are the benchmark for our 3 tasks. And as you can see, here, Compass here is bold, so this achieved here the best result with Pro. Gemini 2.5 Flash, not really, because, sorry, wait a second, come on, disappear, thank you. Last line compass is also bold, great. But if we go now and we go a step up in the complexity, we have now established research agent, like the old DeepSeek, and they use here not GPT-5, but here O3, okay, from OpenAI, and they say, okay, those are the tools that were available. You see there's different sequence of tools now with the terminal, great. Those are the tools, and you see here with Compass, then if we have this in test time, it is only in 2 out of 3 here achieving here the best result, because in this particular task, deep research here OpenAI is a little bit better than this new Compass of Gemini 2.5 Pro. But if you think about the time and whatever here deep research is doing, and I have particular videos analyzing here the performance of deep research by OpenAI, this is quite impressive with this simple method to come so close. And here, of course, with the Terminus agent, DeepSeek version 3 and everything, great. But for Gaia and Human Last Experiment, you see that our new Compass methodology outperforms here the deep research agents here by OpenAI, although it was just O3. Great. So this thing seems to work. So let's do it. Now, of course, if you are a subscriber of my channel or even a member, a very privileged subscriber, then you know that we already had a video on ACE, Agentic Context Engineering from Stanford here and UC Berkeley. And you see, how does it compare? What happened? You see, just 3 days ago, October 6th, tell me. Now, in the video, I didn't just use ACE, but I used here from the Meta and Superintelligence, the agent learning via the early experience, here the supervised fine-tuning that was so important to optimize here the input to ACE for self-learning multi-agent system. And now we have Compass. Now, Compass, if you think about it, is real close, no? Compass and ACE rejected the classical single agent, single context model. Both try to solve here the complex problems of a long horizon reasoning trace by creating a multi-component system where different agents or different modules, in ACE it's called a module, are responsible for doing, reflecting, and remembering. Those are our 3 agents or 3 modules. You see, almost identical, no? Compass, main agent, meta, single context, ACE, generator, reflector, curator, as explained in my video on ACE. Now, let's have a closer look. So what is ACE exactly doing here? It's presented here as an offline inter-task learning framework. So, main goal is to build a reusable playbook, either for memory or whatever, by learning from many different tasks over time. It's a self-learning system. And not to have here the catastrophic forgetting or here the model collapse, as I explained in my video, the curator makes now permanent delta updates to master here the knowledge base that will be used in all future tasks. A self-learning system starts to learn. Compass is very similar from its procedure, but from its strategic orientation as an element in AI, it is different. Because Compass is an online intra-task control framework. Its main goal is to successfully guide an agent through a single, complex, long-horizon task. And the context manager generates temporary briefs to evolve from turn to turn, so trying to solve one single problem. So you see, Compass has a different architectural objective than ACE from Stanford. The final output is also different. The final output of ACE Curator module is a permanent update of the structured playbook, your memory trace, a piece of wisdom that is saved and carried forward indefinitely because you want to have continuous learning for this multi-agent system. The final output of Compass Context Manager is an ephemeral context brief optimized for the next immediate step of the current task. And since English is my third language, I have to look up what does it mean, ephemeral, having a short lifespan. So you see, it is different. And at this moment you might say, no, listen, no, don't do it. And I say, well, wait, if I would theoretically start to think now on my own, And I think, if I have a new method as presented in this video to solve now a single task complexity like compass, so doing just a single job, and then for my last video I have the ACE method to memorize now multitask complexity reasoning traces to how to solve multiple jobs, and they are stored now in my memory or somewhere else. I say, can I combine this? So yeah, let's do it. Let's think. So in this video, I did not just look at ACE, but I needed here for me to superintelligence here the early experience as the input optimization to ACE. And now let's think about this. Can we do the same with compass on a different complexity level? You might say. So if we start now a new difficult task using here the compass architecture. Now this is here for a single temporary task. So let's start with this. So its main agent, the meta thinker, and the context manager work together to solve the problem, dynamically evolving the context brief from turn to turn, and our worker B is doing the work. And after the task is completed, either we have here from the meta thinker the success or the failure command, the entire compass trajectory, including here the main actions, the meta thinking strategic decision, and the context manager brief. This is available now in Compass. Now, what do you think we just take this and we pass it on as a fresh input to the ACE framework? Because think about it, what it does, it explains exactly what ACE needs now for a single job, the perfect optimization for a single job, given we have 5 or 7 different tools available. And now, if we have now not superintelligence meta input here for the agent learning, but we have here all the actions, all the strategic decisions, everything that happened in context with the real environment, and then the manager brief, and then the successful reasoning trace, and we feed this in now to the reflector module from ACE, it can now analyze this rich data and distill here a permanent, a strategic lesson, and not just that it generates now a reward signal or a binary reward signal, but we go now to a higher natural language complexity. We have now as a strategic lesson, given here that you have a powerful LLM that is able to understand this and create an insight. Now this insight might be, hey, the meta thinker correctly identified here looping behavior and the solution was to do A, B, C. This is now a generalizable pattern that will provide an input. So the reflector comes back and says, hey, I found a new pattern for my LLM, and you know LLMs are stupid and are just pattern generation and pattern analysis machines. So the creator of ACE takes up these lessons and makes it now a permanent delta update. I explained this in my video, what this is and how it is done in the memory, to the agent's master playbook. So making now the entire system smarter for the next time it encounters here a similar job, a similar situation, a similar complexity. So if I look at this, and yes, this is human thinking, careful, this is not AI, it looks like we could use here Compass also as an input to the ACE complexity, the solving complexity of ACE. So then we would say, hey, Compass, if you want, is a high-performance engine. Let's say it's a car, yeah? Given here this example, that navigates here on some treacherous road of a single complex query in an abstract space. ACE, on the other hand, is this expert engineering team, at home in the garage with all the telemetry from the car, completely understand where the car is, what is happening to the car, what is happening to the car's engine, to the suspension, what is happening at velocity, acceleration, everything. It analyzes the complete telemetry for this agent on the road, solving here the complex query, and can now learn from this single task and upgrade here the engine parameters for all future races. So you see, human interaction can bring this up. And of course, slowly we are moving here really into self-learning agentic systems, multi-agent system, where we do have constant contact with the environment. We have the possibility. We have built an algorithm that is continuous self-learning, uploading here to memory, building here those playbooks from all the experience that it learned, like a little child that it learns how to behave in the world. And you might say here, hey, wait a minute, this was trivial. No, there was no complexity at all. Why did Google and Stanford and UC Berkeley took so much time to solve here this? No? Is there nothing more challenging on your YouTube channel here, Discover AI? Well, if you want to challenge me, okay, let's do this. Now, as an outlook here for the next weeks, LLMs face problems. And if you remember, may have already maybe seen this member-only video, reg output flips when certain text passages are reordered because we have problems. The fine-tuning methods eroded the invariance we have in our transformer traces that are learned at pre-training because we have problems. The chain of thought prompts take a path-dependent routes, and the compiler fusion or the reordering perturbs here the logics near the decision boundaries and can flip complete decisions by the AI. And all these failures we cannot solve today. We cannot even detect those failures in their system complexity as a complete system. These failures violate intended invariances of our transformer system, break the continuous integration of new data, new knowledge, and force our developer teams here to trade here safety for speed. Now, if you want a challenge, hey, what do you think about this publication? October 9, 2025. Inverse-free Wilson loops for transformers. Quotation mark. Practical diagnostic for invariance and order sensitivity of transformer architecture. Now, this is by Stanford University, and here, what is this? University of Illinois, Champaign something. Here you have it. This is exactly, if you say, hey, this is nonsense, why you get this idea? Everything is perfect in AI. Nobody here on X or anywhere posts that we have problems in AI, no? Look at this. Here Stanford tells us really clear. Language models can change answers under harmless edits that matter in practice. Reg output flip when passages are reordered. Fine-tuning erodes the invariances learned at pre-training. Debate or chain of thought prompts take path-dependent routes suddenly, and compiler fusion or reordering perturbs the logic near the decision boundaries. These failures violate intended invariances, break the continuous integration, and force teams to trade safety for speed. It is so nice to see on the latest research what problems we are currently facing with AI systems. Maybe you are not reading this in your literature. And they use here, hey, let's measure your holonomy. And you might say, what? Now, luckily, I would now recommend to you, maybe you have a better source, then please also share this with the community. The makers of Mathematica, and from Wolfram Alpha, there's Wolfram Mathematical World. And I found they have a real good explanation of all the mathematical complexity you're going to encounter in this new preprint. Holonomy group, Riemann manifold, tangent vector, move along path, parallel transfer, vector addition, scalar multiplication, linear maps, tangent vector, possible closed loop, parallel transfer, group, holonomy group definition, Riemann metric, orthogonal group, orientable, Orient manifold has a subgroup. Beautiful. Yeah, also contains topological information, more about this later. But if you want to read this paper, it is a paper that is quite challenging. And maybe if I got some question, hey, do I really need to study mathematics for AI in the future? Come on, everything is solved for AI. Have a look at this paper. They look at the current problems that nobody can solve, and they try to solve this with some very interesting mathematical approaches. They have here chapter 4, geometry-based diagnostic. They go here and they try to explain this with commutators as order-sensitive diagnostic systems. Or then here, fiber bundle perspective, discrete transport, and holonomy. This is not trivial at all. Have a look at this paper if you just want to get a feeling. You don't have to understand it at the first time, maybe. Of course, if you have a PhD in mathematics, you say, hey, yes, I can build on this. I can further go with new ideas. But just to give you an idea, why do you need mathematics? Why mathematics is still so important for the next development step in AI. We have an unbelievable open space that we have to explore here in the next years in AI. And there are challenges all over the place. So if you want to invest your time in mathematics, theoretical physics, whatever you like, maybe do a PhD in computer science, I think it's really worth your investment, because things will not stay as simple as they are today. The complexity, especially the mathematical models for AI, will continue to improve, will continue to become more and more complex. And I can tell you from my experience, it is harder and harder to find simple explanation for all the papers that are coming out every single day. So I can tell you all the publications, they really make here a jump in the quality, but also in the mathematical complexity if you really want to understand the insight, the hidden ideas. And this is why I try here to present to you the hidden ideas at the very beginning of my videos. So therefore, just to give you a feeling, if you have some time and you say, hey, how are current researchers trying to solve the problems we have with AI? Maybe this would be a great additional reading, maybe for the weekend. I hope you enjoyed it. I see you in my next video.